Greetings, my mathematical Padawans. Welcome to Lesson 4.1, Graphing Polynomials. So in the last chapter, we were doing a lot of talking about quadratic equations. In this chapter, we will kick it up a notch, if you will, and increase the degree or increase the exponent that we're talking about and make the highest exponent anything that we can think about. And these are called polynomial equations. A polynomial is, by definition, a monomial or the sum of the monomials. And a monomial just means one term, okay? You gotta look at the prefix, right? Poly, right? The prefix poly means many. And of course, mathematically, nomials would mean, in our case, terms. So a polynomial has many terms. So if you think of like a quadratic equation, right? A quadratic equation we would write in the form like f of x equals 2x squared minus 7x plus 3. That is, by definition, a polynomial. It has many terms. As a matter of fact, it has one term, two terms, three terms to it. And of course, a polynomial can have even more than that. The sky's the limit as far as what that goes. You don't have to be too concerned with this generic formula for what a polynomial actually looks like. There's just some important things that we need to identify from it. Like, for example, when we write our exponents, we always put them in descending order, right? So when in standard form, exponents go from highest to lowest. So that's all that these exponents up here actually mean. It means, hey, I'm going to put them with the highest exponent first and the lowest exponent last, or the constant that doesn't have anything at the very end. Another important characteristic is that all of the coefficients, that means all of the numbers that are in front of my variables, have to be real numbers. So no imaginary numbers. That's the really good news for you. No imaginary numbers will come up in this particular chapter at all, as a matter of fact, until the very end at least. And all of my exponents have to be positive integers. So these exponents, not only do they go from highest to lowest, you will also not find any negative exponents at all. Beyond that, when it's in that standard form, whatever the first number we see, we call that the leading coefficient. So in my example that I wrote down here at the bottom of the page, my leading coefficient would be the 2 that's right there. The degree is the highest exponent. So whatever the highest exponent you see in the whole problem, that's the degree. Again, in my example problem, that just also happens to be 2 as well. Okay, and then the constant term, that's the thing that's left over at the end. So in my example problem, that would be the positive 3 that I had left over at the end. They're important things to be able to pull out and look at because they direct us, they give us things to do. We also can name polynomials. So this chart right here kind of gives you the type of equation and then an example. So we classify our polynomials based upon the degree. So if it has, for example, a degree of 2, we know that that is a quadratic equation. If it has a degree of 3, it's called a cubic. Do you see how the highest exponent over here is a 3? That's a cubic equation. And of course, if it has a degree of 4, like a quarter, we call it a quartic equation. And again, I think these examples over here are really good. Maybe you want to pause the video right now and see whether you can take a look at some of these examples a little closer, because I did go through that very fast. So we're going to take a look at these 4 examples, and we're going to see if they're a polynomial or not, and we're going to identify it. If it is, we're going to identify the degree and the leading coefficient of that. So remember, a couple characteristics that we have to be on the lookout for. Remember, all coefficients are real numbers, okay, no imaginaries. All exponents are positive integer values. It doesn't necessarily have to be in standard form, but that's definitely what's going to help us identify the degree and the leading coefficient. Why don't you real quick pause the video right now and see how many of these you can get right without actually seeing one done. Now, of course, if you need to see one done, I'm going to do that here in a second. But pause the video, see how many you can get right on your own. Okay, so let's take a look at A. F of x is equal to negative 4x to the 5th plus 7x squared minus 2. So let's see here. Do we have all integer coefficients? Yes, we do. Are they positive? Yes, they are. Great. So that checks out. What about the numbers in front of those variables? Are they integer values? Are they real numbers? Yes, they are. So we're good to go. So this is in fact, A is in fact a polynomial. So we'll give that a big check mark. Yes, it's a polynomial. So because of that, we can identify the degree and the leading coefficient. So that's here. Whoops. Degree. The degree is the highest exponent. So if I look at this whole problem, the highest exponent is right here. So my degree is equal to 5. And what about the leading coefficient? The leading coefficient would be the number in front of the highest exponent. So you see the number 5 here? So the number that's right in front of it, -4, that's going to be the leading coefficient. Let's go on to B. Is this in fact a polynomial? Well, let's see if it checks out. Let's see. So we'll look at the numbers, or we'll look at the exponents. Are the exponents positive? Integers? Yes, they are. What about the numbers in front? Are they real numbers? Oh yeah, the square root of 3. Okay, so that's not a rational number, but it is a real number. So guess what? B is a polynomial equation. So that gets a big old check mark next to it. Okay, and let's see here. Can we identify the degree? Well, that's the highest exponent. Ooh, right there, it's 4. Double check, it's not always the first thing you see. What about the leading coefficient? Let's see here. Well, it's going to be the number that's right in front of the highest exponent. So that is, in fact, the square root of 3. What about letter C? Let's go on to letter C. Is that a polynomial equation? Well, let's check out the exponents. Uh-oh, look here. -2. -2. That's no good. So this is not a polynomial. Not a polynomial. So because it's not a polynomial, there's no need to identify the degree or the leading coefficient. Let's go on to D. What about D? Let's check out the exponents. Ooh, I have a variable in an exponent. That's no good. So this is not, because of that term right there, this is not a polynomial. All right, let's go on. So the directions here say evaluate f of x. When f of x is equal to -2x to the 4th plus 6x to the 3rd minus 3x plus 11 when x is equal to 4. Okay, folks, this is nothing that is new. This is absolutely nothing new. We want x to equal 4, so we're going to take and we're going to plug 4 into my expression. So that's here. That's -2 times 4 to the 4th power plus 6 times 4 to the 3rd power minus 3 times 4 plus 11. And now, folks, I'm going to use a calculator for this. Right? I'm going to type it all into my calculator all in one time because I'll be sure to get it right. If we were doing it by hand, it's really important that you do exponents first. So I'm going to go through and I'm going to actually do this 4 to the 4th power. So that would give me -2 times, let's see, 4 to the 4th power, 256, plus 6, and then we got 4 to the 3rd power. That's 64. Okay, then we got -3 times 4. Yes, I'm just going to keep it there. That's no exponent there, but I'll keep it right there. And then plus 11. Now I'll go through and do that multiplication. -2 times 256 is -512. Plus 6 times 64, that's 384. 3 times 4, -12. Plus 11, I end up with a final answer of -129. That's nothing different than things that we've been able to do before. So we can elevate that. So now we're going to create a table of values for a polynomial. Now, folks, this is where it gets a little bit, maybe, we got to be careful, right? We can actually pick whatever numbers we want to for a polynomial. When we're typing in a graph, it's not going to be quite as nice as our quadratic. We're not going to find the same characteristics as what we did before. But I'm going to plug in a bunch of different numbers. Maybe I'm going to type this equation into Desmos. I'm going to use that table feature to come up with a table of values. Maybe I'm going to evaluate each one of these individually. I'm going to use something to help me come up with the answers when I plug in these individual values. I mean, a scientific calculator will absolutely do the work for us when I plug those numbers in. 6. Okay, so I'm just coming up with that. So now it's about taking these numbers and we're going to plot them on a coordinate plane. Now, I did that a lot nicer on the previous page. So let me show you what happens when I take that table of values and I plot them on a coordinate plane. So again, here you'll see that same table of values from the previous slide, and you'll see when I plot those points, what I end up with. Got to be really careful because with a polynomial equation, there's not really any pattern to what we're going to see here. It becomes a little bit more difficult. So we're definitely going to have to rely on Desmos to help us come up with the shape of this graph. There are some characteristics that we'll learn along the way, but really we're going to rely on Desmos to graph this. So what you'll find is when you actually type this into Desmos, you'll see that the graph looks a little something like this. Now I'm going to be not 100% exact with that because Desmos will do a much better job, but it's all about connecting the dots and making sure that we have an idea of what this graph looks like. One of the things that's really interesting is here on the ends of my graph. So like over here on the left end of this graph, I think it's really important for you to know that these values get smaller and smaller and smaller. That's why I've drawn the arrow on the end of that line. Because as the x values get smaller, the y values also get smaller. And on the other end, the top right corner of my graph, I think it's important for you to also note that as my x values get bigger, my y values also get bigger. And these arrows, these blue arrows that I've put on the end, describe something called end behavior. And there's rules that actually dictate what the end behavior of the function is actually going to be. And those rules look a little something like this. You'll notice that they mainly revolve around the degree and the leading coefficient. So when the degree is odd and the leading coefficient is positive, you'll notice that the two ends point in opposite directions. The left end points down and the right end points up. But if the degree is odd, see they're both odd, but the leading coefficient is negative, you'll see that the left side points up and the right side points down. What happens in the middle, it doesn't really matter. That varies from function to function. We're talking about just the two ends of the function. Now, if the degree is even, both ends point in the same direction. Either both ends will point up if the leading coefficient is positive, or both ends will point down if the leading coefficient is negative. This characteristic is really important, especially when you're creating a table of values, to make sure that your table of values shows you everything that you want it to show you. So let's practice using those rules right now. So what would the end behavior of the graph negative 0.3 x to the third plus 1.7 x squared minus 4x plus 6b? Well, folks, all of this stuff down here doesn't really matter. We're really going to look right here at the degree, which is 3, and the leading coefficient, which is negative. I don't even care what the number is. I just care that it's negative. So based upon that, if I go back and look at my previous rules, which are right here from the previous slide, you will see that if the degree is odd, okay, so that's either here or here, and the leading coefficient is negative, so that's here, my two ends look like this. So my function would be up on the left side and down on the right. Now the fancy way to write that are these terms right here. We would say f of x, that's the y values, approach positive infinity. That's like pointing up. As x goes towards negative infinity. That's like saying the left side. And down, well, that's pointing towards the down. So that's f of x going towards negative infinity as x goes towards positive infinity. That x going towards positive infinity is like saying the right side. So again, f of x as x approaches positive infinity says up. That's like the same thing as saying going up. As x goes towards negative infinity, that's saying like the left side. And then down, that's f of x goes towards negative infinity as x goes towards positive infinity. And you can see all those individual rules are right here on my previous page that you saw. Hopefully you wrote those down when you did those. If not, take the opportunity to do that now. So why don't you take a minute right now, pause the video, and try out these 3 problems. Take a look to see if you can evaluate number 1 and 2 at those particular values. And then for number 3, see if you can describe what the end behavior of that function will be. Pause the video, and then we'll go over these briefly. So for number 1, all we're going to do is we're going to plug the number 4 in for x. So that gives me negative 4 to the third power plus 3 times 4 squared plus 9. Let's see here. 4 to the third power is negative, or it would be 64, so we put that negative in front of it. Plus, let's see here, 3 times 4 squared is 16 plus 9. And when I do all that math together, I end up with the value of negative 7. For number 2, we're going to do a similar thing. We're going to take that negative 2 and we're going to plug it into my expression. So that's 3 times negative 2 to the 5th power minus negative 2 to the 4th power. Please notice how I put that negative 2 in the parentheses. Times 6 times negative 2 plus 10. We'll go ahead and do the math here. So let's see here. Negative 2 to the 5th power is negative 32. And then minus, let's see here, negative 2 to the 4th power is 16. So that would be minus 16. Then I have negative 6 times negative 2, which would be plus 12. And then plus 10. When I do all of that math together, I'll get negative 90 as my final answer for number 2. And for number 3, we're going to go back to that table and use that, where we're going to identify the degree and the leading coefficient. So for this problem, we know the degree is odd, and the leading coefficient is positive. So when it's odd and positive, I know my two ends of my function. The left side points down and the right side points up. So let's say we're down on the left side, but we're up on the right. Now, if you wanted to go back and use the fancy terms, we would say f of x approaches negative infinity as x approaches negative infinity, and f of x approaches positive infinity as x approaches positive infinity. All right, let's take a look at another problem. For the final problem, we're going to try to create a graph that has all 4 of these characteristics. So we want to draw something, we want to draw a function that is increasing when x is between negative 2 and 3, and then decreasing when x is less than negative 2 and x is greater than 3. And then when my function is greater than 0, when x is less than negative 4 and between 0 and 5, and f of x is less than 0 when x is between negative 4 and 0, and x is greater than 5. So I know, like, if you're reading that, that can really seem very overwhelming at first. So let's take it step by step and try to figure out exactly what it is that's going on here. So my x value is between negative 2 and 3. So negative 2 is here, and 3 is here. So along that green area, in this green area of my graph, let me just draw the whole thing in there, right? In this green area of my graph, f has to be increasing, means it's going to be going up. So my function is going to be increasing in this area. It's increasing here. And that means when x is less than negative 2, so that is this region here, right? This region here. That region there, and then when x is greater than 3, so that's this region here, right? This region right in here. My function is going to be decreasing, or going down. So I'm going to be decreasing here and decreasing here. Okay, next part. F of x is greater than 0. Okay, what the heck, what's that mean? That means that the y values are greater than 0. To say it a different way, that means that I am above. This means I am, this right here, that means that I am above the x-axis, right? My y values are positive. And the second part right here, less than 0, that means I'm below the x-axis, or my y values are negative. Well, sorry about that. I spelled below wrong. It's B-E-L-O-W. Sorry about that. Anyways, so when x is less than negative 4, so what that means is, like, at negative 4, at the value of negative 4, that means I'm not above the x-axis or below the x-axis. Okay? And then at 0, same thing. I'm not above the x-axis or below the x-axis. Same thing at 5. So what that kind of gives me a hint of is that gives me a hint of where I'm going to change from being above the x-axis to below the x-axis. Now everything else is just kind of like, you don't have to be too specific with what's happening necessarily. So I know that I'm going to be increasing in this or decreasing in this yellow area. And I got to be above the x-axis here when I'm less than -4. So that means my function is going to do something that looks like this, right? Because that is decreasing and above the x-axis. And then I'm going to be continuing decreasing. See, I'm keep going down, and I'm going to go down until I get to here at -2. Once I'm at -2, my function can no longer decrease. Now it has to increase, has to go up. So here I am going up, and I have to be below the x-axis until I get to 0. And now that I'm at 0, now I'm going to continue to increase, but now I am above the x-axis. And I'm above the x-axis and increasing until I get here to 3. And once I'm at 3, I can no longer be increasing. My function has to decrease. So my function is now going to go down, but I'm still above the x-axis until I get to 5. And once I'm at 5, I then am below the x-axis and will continue to decrease. I could put little arrows on the end if I wanted to. So we just kind of got to think ourselves through that. Think about what that actually means. When am I above the x-axis, below the x-axis? When am I increasing? When am I decreasing? And I think breaking it up into these different regions is helpful for you to figure out what this curve may look like. Now yours doesn't have to look like that, right? We could have gone lower here or higher up here, but fundamentally these points where it crosses the x-axis and what the ends look like are very important for this function. All right, folks, that's all I have for you tonight. So good luck, and we'll see you tomorrow in class.